Alright, here's the thing about Pythagoras. And I need you to forget everything you think you know from high school geometry for just a moment. Yes, you know the theorem. A squared plus b squared equals c squared. You've probably used it to calculate distances, maybe even to help hang a picture frame straight. But here's what blows my mind about this guy. Pythagoras didn't just discover a mathematical formula, he created an entire way of seeing reality. Picture this. It's the 6th century BC. Most people think the world is controlled by capricious gods who play with human lives like children with toys. And then comes this mathematician who says, wait, what if everything, and I mean everything, follows mathematical laws? What if the universe isn't chaos, but harmony? What if numbers are the language God speaks? This is revolutionary. This changes everything about how we understand our place in the cosmos. Pythagoras isn't just doing math homework, he's proposing that reality itself is mathematical. That truth can be discovered through reason, not just revealed through religion. And here's what's remarkable. He was right. Not completely, not in every detail. We'll get to his weird ideas about beings and reincarnation later, but fundamentally, profoundly right. Modern physics, astronomy, even music theory, they all rest on this Pythagorean insight that mathematics describes the structure of reality. So when we say we're studying the man, the myth, the mathematician, we're not being cute with alliteration. We're acknowledging something genuinely strange. Pythagoras is all three. There's the historical person, the legendary figure who supposedly had a golden thigh and could be in two places at once, and the brilliant mathematical mind whose work we still use 2,500 years later. Our job today is to separate these three, to understand who Pythagoras actually was, what he discovered, and why it still matters to your life right now. Let's start at the beginning. Around 570 BC, that's about 2,600 years ago, a child is born on the Greek island of Samos. This is important, so stay with me here. As you can see here, his father Menisarchus was a merchant from Tyre, a Phoenician city. Now, the Phoenicians were the master traders of the ancient world. They sailed everywhere, knew everybody, had connections across the Mediterranean. This isn't some isolated Greek farmer's son. This is a kid who grows up hearing stories about Egypt, Babylon, Persia, all these different cultures with their own mathematical and philosophical traditions. His mother, Pythagoras, was a native of Samos. And here's what we must carefully consider. Samos wasn't just any island. This was one of the intellectual centers of the Greek world. The tyrant Polycrates had turned it into a cultural powerhouse. There were engineers building incredible aqueducts, architects designing magnificent temples, astronomers studying the stars. Think of it like this. If ancient Greece was like modern America, Samos was Silicon Valley. This is where smart people went to do cutting-edge work. Pythagoras didn't just happen to become brilliant, he was born in exactly the right place, at exactly the right time, to exactly the right family to make it possible. But here's where it gets interesting. Being born with advantages doesn't make you great. Plenty of merchants' sons in Samos probably became, well, merchants. What makes Pythagoras different is what he does with these advantages. And what he does is leave. He doesn't stay comfortable on his home island. He goes searching. And this is where our story really begins. Because the education Pythagoras receives will shape not just his own thinking, but the entire Western intellectual tradition. Throughout history, philosophers have grappled with this question. Where does knowledge come from? Is it revealed by the gods? Inherited from tradition? Discovered through reason? Pythagoras is about to give us an answer that will echo through the millennia. You go find it. You study with the best minds you can find wherever they are. So let's follow young Pythagoras on his intellectual journey, because understanding where his ideas came from helps us understand why they were so revolutionary. Okay, so here's where young Pythagoras becomes the intellectual equivalent of a world traveler. And I want you to understand just how unusual this is for the time. Look at this progression. Greek education, Egyptian wisdom, Babylonian knowledge. This isn't a semester abroad. This is decades of his life, traveling thousands of miles, learning from completely different civilizations. In an age where most people never left their hometown, Pythagoras is crossing the Mediterranean like he's collecting degrees from different universities. First, Greece. He studies with Thales and Anaximander, and these names should mean something to you. Thales is often called the first philosopher in Western tradition. He's the guy who said, maybe we should explain the world through natural causes instead of just saying Zeus did it. Anaximander took it further, proposing that the universe operates according to rational principles. So Pythagoras is learning from the cutting edge of Greek rational thought. He's getting the foundation in mathematics and philosophy that will shape everything he does later. But then, and this is crucial, he doesn't stop there. He goes to Egypt. Now, the Greeks had enormous respect for Egyptian learning. They considered Egypt the ancient repository of wisdom. And what does Pythagoras study there? Geometry and religious practices from the priests. Think about that combination. He's not just learning math as abstract theory. He's learning how the Egyptians used geometry to build the pyramids, to survey land after the Nile floods, to create their magnificent temples. And he's learning their religious mysteries, their ideas about the soul, about the afterlife, about the divine order of the cosmos. Imagine being a young Greek guy, probably in your 20s, sitting in some ancient Egyptian temple while priests who trace their lineage back 1,000 years teach you sacred geometry. You'd come back changed, right? You'd come back thinking, oh wait, maybe mathematics isn't just practical, maybe it's sacred, maybe numbers reveal divine truth. And then Babylon. He studies astronomy and numerical systems. Now, the Babylonians were the master astronomers of the ancient world. They'd been tracking planetary movements for centuries. They had sophisticated mathematical systems. They used base 60, which is why we still have 60 seconds in a minute, 60 minutes in an hour. Here's what blows my mind. Pythagoras is synthesizing all of this: Greek rational philosophy, Egyptian sacred geometry, Babylonian astronomical mathematics. He's taking the best of 3 major civilizations and asking himself, what connects all of this? What's the underlying truth? And the answer he arrives at, the answer that will define his entire philosophy, is this: mathematics is the universal language. It works in Greece, it works in Egypt, it works in Babylon. Numbers don't change based on your culture or your gods. 2 + 2 = 4 whether you're in Athens or Thebes or Babylon. This is the birth of the idea that there are universal truths accessible to human reason. This is the foundation of science as we know it. So after all these years of travel and study, Pythagoras comes home. It's around 520 BC. He's probably in his late 40s, early 50s. He's learned from the greatest minds of 3 civilizations. And he's ready to teach. He establishes what's called the semicircle school on Samos. Now, we don't know exactly what semicircle means here. It might refer to the shape of the building, or maybe the seating arrangement, or perhaps it's symbolic of something. But what we do know is that he's gathering students and sharing everything he's learned. Picture this. You're a young person on Samos, and suddenly there's this guy who's been to Egypt and Babylon, who studied with the great philosophers, who knows mathematics and astronomy and music theory and philosophy. And he's teaching. He's not keeping this knowledge secret. He's saying, come, learn, understand the mathematical structure of reality. But here's where things get complicated. Samos at this time is ruled by a tyrant, and not the fun kind of tyrant. We're talking about Polycrates, who's consolidating power, who's suspicious of intellectuals, who doesn't like the idea of people gathering to discuss philosophy and mathematics. As you can see here, Pythagoras faces political opposition from the government, and we need to understand what this means. In the ancient world, philosophy wasn't just abstract thinking. Philosophy was about how to live, how to organize society, what justice means. Teaching philosophy was inherently political, and Pythagoras isn't just teaching mathematics. He's teaching that there's a rational order to the universe, that truth can be discovered through reason, that there are principles of harmony and justice that transcend the whims of tyrants. You can see why Polycrates might find this threatening, right? It's the eternal problem of the intellectual. You spend years learning profound truths about reality. You come home excited to share them, and the government says, actually, we'd prefer if you didn't encourage people to think too much. It's inconvenient. So Pythagoras faces a choice. He can stay on Samos, compromise his teaching, work within the constraints of tyranny, or he can leave again. He can go somewhere where he has the freedom to teach what he believes is true. And this is where our story takes its most important turn. Because what Pythagoras does next, where he goes, what he builds, will create one of the most influential intellectual communities in human history. He looks across the sea to southern Italy to a place called Croton, and he makes a decision that will change everything. But before we get to Croton and the founding of his famous school, I want you to appreciate what we've just witnessed. We've seen a man who refused to accept the limitations of his birth culture, who sought wisdom wherever it could be found, who synthesized diverse traditions into something new. And now, faced with political opposition, he's about to do it all over again. But this time he's going to build something that lasts. So Pythagoras sails to Croton in southern Italy, what the Greeks called Magna Graecia, Greater Greece. And I need you to understand, this isn't retreat. This is strategic repositioning. He's not running away from Samos, he's running towards something. Look at this progression: relocation, new academy, diverse following. Around 518 BC, he arrives in a city that's wealthy, cosmopolitan, and crucially free. No tyrant breathing down his neck. No political interference, just opportunity. And what does he do with this freedom? He establishes a school that combines philosophy, mathematics, and religious practices. Now we must carefully consider what this means. This isn't a university in our modern sense. This isn't even like Plato's academy, which will come later. This is something entirely new, a community where intellectual inquiry and spiritual practice are inseparable. But here's what absolutely blows my mind about this. And this is where Pythagoras shows he's not just brilliant, but genuinely radical for his time. He accepts both men and women as students. Let that sink in for a moment. We're talking about the 6th century BC. Women in most Greek cities can't own property, can't participate in politics, are barely educated beyond household management. And Pythagoras says, if you can think, you can study mathematics. If you can reason, you can pursue philosophy. I mean, think about how progressive this is. We're 2,500 years later, and we're still fighting about women in STEM fields. Pythagoras solved this problem before Socrates was even born. He looked around and said, you know what? Intellectual ability has nothing to do with gender. Who knew? We know the names of some of these women. Theano, who may have been his wife, was a mathematician and philosopher in her own right. She wrote treatises on mathematics, physics, medicine, and child psychology. There's Damo, possibly his daughter, who preserved his teachings. Arignote, who wrote on sacred rites and mysteries. These weren't just students sitting quietly in the back. These were active participants in one of the most important intellectual communities in the ancient world. And this tells us something profound about Pythagoras' philosophy. Remember, he believes mathematics reveals universal truth. Well, if truth is universal, then it's accessible to everyone who can reason. Gender doesn't matter. Social class doesn't matter. What matters is your willingness to think, to question, to pursue understanding. So he's got this school in Croton. He's teaching mathematics, philosophy, music theory, astronomy. He's got men and women studying together. And the school is growing. People are coming from all over the Greek world to study with him. But Pythagoras doesn't stop there. Because what he creates next isn't just a school. It's a way of life. Now we need to talk about what made the Pythagorean community so unique and so controversial. Because this wasn't just about showing up for lectures and going home. This was total commitment. Look at these 4 elements: community living, strict discipline, knowledge protection, interdisciplinary approach. Each one of these is radical. Together, they create something that's part university, part monastery, part secret society. Community living. Members shared possessions and lived together in a commune-like setting. Imagine that. You don't just study with Pythagoras, you live with the Pythagoreans. You eat together, sleep in the same buildings, share your resources. It's like joining a philosophical kibbutz. And yes, before you ask, this created exactly the kinds of problems you'd expect when you put a bunch of intellectuals in close quarters. We have records of disputes, arguments, people getting on each other's nerves. Turns out even ancient philosophers couldn't agree on who forgot to do the dishes. But here's where it gets intense. Strict discipline. They observed dietary restrictions. Famously, they wouldn't eat beans, though we're still not entirely sure why. Some say Pythagoras thought beans contained souls. Others say it was about flatulence interfering with meditation. The ancient sources disagree, which is kind of hilarious. They had periods of mandatory silence. New members, the akousmatikoi, the listeners, had to spend years just listening to lectures without speaking. They couldn't ask questions, couldn't debate, couldn't even see Pythagoras directly. He taught from behind a curtain. Why? Because Pythagoras believed you had to discipline your body and your mind before you could truly understand mathematical truth. You couldn't just intellectually grasp these ideas, you had to live them. Your whole life had to be ordered according to mathematical harmony. And then there's the knowledge protection. They maintained secrecy about mathematical discoveries and philosophical teachings. This is where things get ethically complicated, and we need to think carefully about this. On one hand, Pythagoras is teaching that truth is universal and accessible to reason. On the other hand, he's saying, but we're not telling everyone everything we know. There's an inner circle, the mathematikoi, the learners, who get the advanced teachings, and there's an outer circle, who get the basics. This creates a fundamental tension in Pythagorean philosophy that never gets fully resolved. Is knowledge democratic or aristocratic? Should wisdom be shared freely or guarded carefully? And here's what's fascinating. We're still arguing about this today. Should advanced scientific knowledge be public? Should there be secrets? Who decides? It's like the ancient Greek version of academic paywalls. Yes, we've discovered profound truths about reality. No, you can't read the full article unless you're a member. Please subscribe to Pythagorean Premium for full access. But there was a serious reason for this secrecy. Pythagoras believed that mathematical knowledge was sacred. These weren't just formulas. These were insights into the divine structure of reality. And sacred knowledge, he thought, required preparation. You couldn't just hand someone the keys to the universe without ensuring they understood the responsibility that came with it. And this brings us to the fourth element, the interdisciplinary approach. Mathematics, music, philosophy, all integrated as interconnected disciplines. This is where Pythagorean education becomes truly revolutionary, because Pythagoras doesn't teach math on Monday, music on Tuesday, philosophy on Wednesday. He teaches that they're all the same thing. Mathematics describes musical harmony. Musical harmony reflects cosmic order. Cosmic order reveals philosophical truth. Everything connects. The ratio that makes a pleasing musical interval is the same kind of mathematical relationship that governs planetary motion. The geometric proportions that create beauty in art reflect the same principles that structure the cosmos. Study one deeply enough, and you understand them all. This is the birth of what we might call unified theory. The idea that there's one underlying mathematical structure to all of reality. Einstein spent his later years searching for this. Physicists today are still looking for a theory of everything. Pythagoras believed he'd found it. Number is the essence of all things. So imagine being part of this community. You wake up, you meditate, you study geometry, you practice music and discover it's really mathematics. You discuss philosophy and realize it's really about mathematical harmony. You look at the stars and see mathematical patterns. You live with people who share this vision, who are all pursuing the same understanding. It's intoxicating. It's transformative. And it's also, we need to be honest here, it's a little bit cult-like. Because here's the thing. When you combine total commitment, shared living, strict discipline, secret knowledge, and a charismatic leader who claims to have special insight into the nature of reality, well, that can go really well, or it can go really badly. And for Pythagoras and his followers, it's going to do both. The Pythagorean Brotherhood will produce some of the most important mathematical discoveries in history. They'll influence philosophy for millennia. But they'll also create enemies, trigger political backlash, and ultimately face violent persecution. But before we get to the downfall, we need to understand the achievements. Because what the Pythagoreans discovered, what they proved and taught and passed down, that's what survives, that's what matters. That's what we're still using today. Alright, let's talk about the theorem, and I know what you're thinking. Oh great, A2 plus B2 equals C2. I learned this in 8th grade. Can we move on? No, we cannot move on. Because I need you to forget everything boring you ever learned about this formula and see it the way Pythagoras saw it, as a window into the fundamental structure of reality. Look at this. 3 parts, the formula, the historical context, the mathematical impact. Let's start with what you think you know. The formula. In a right triangle, the square of the hypotenuse equals the sum of the squares of the other 2 sides. A2 plus B2, Archer, C2. Simple, right? You can calculate it. You can prove it. You probably did prove it with little squares drawn on graph paper. But here's what we must carefully consider. Elements of this theorem were known in Babylon and Egypt long before Pythagoras. The Babylonians had clay tablets with Pythagorean triples, sets of numbers that work in this relationship. The Egyptians used ropes with knots to create right angles for building, So what did Pythagoras actually contribute? Here's what's remarkable. He provided the first known proof. Not just, hey, this seems to work when we measure stuff. Not just we've noticed this pattern, but proof. Logical, deductive, mathematical certainty. He showed that this relationship must be true, not just that it happens to be true. And this distinction between empirical observation and logical proof, this is one of the most important intellectual moves in human history. This is the birth of mathematics as we know it. The Babylonians knew that 3, 4, 5 worked. They knew that 5, 12, 13 worked. They had lists of these numbers, but Pythagoras proved that all right triangles follow this relationship. Every single one. Forever. In all possible worlds. Think about what this means. You can measure 1,000 triangles and find they all follow this pattern. That's induction. That's science. But you can never be absolutely certain the 1,001st triangle will work the same way. But with mathematical proof, you know with absolute certainty. Not because you measured, not because you observed, but because it must be true given the logical structure of geometry. Legend says that when Pythagoras proved this theorem, he was so excited he sacrificed 100 oxen to the gods. Now, I don't know if that's true. It seems inconsistent with his whole don't harm living things philosophy, and also, where do you even get 100 oxen? But the story captures something real, the sheer joy of mathematical discovery. And look at the mathematical impact. This theorem formed the foundation for trigonometry and advanced geometry. You cannot do engineering without it. You cannot do physics without it. You cannot do computer graphics, GPS navigation, or architecture without it. Every time you use Google Maps and it calculates the shortest distance between 2 points, Pythagorean theorem. Every time a construction crew ensures a building is square, Pythagorean theorem. Every time a video game renders a 3D environment, Pythagorean theorem. This isn't ancient history. This is the mathematical infrastructure of modern civilization. But here's what Pythagoras really understood, and what we often miss. This theorem isn't just about triangles. It's about the nature of space itself. It's about how distance works, how measurement works, how geometric relationships are structured. When Pythagoras looked at this theorem, he saw proof that the universe operates according to mathematical laws. Not sometimes, not approximately, but exactly, perfectly, eternally, the same way everywhere, always, and if that's true for triangles, why not for everything else? Why not for music, for astronomy, for the structure of matter itself? This is why the Pythagorean theorem matters, not because you need to calculate the length of a ladder, but because it's evidence that mathematics describes reality at the deepest level. But Pythagoras and his followers didn't stop with triangles. Oh no. Once you start seeing mathematical patterns everywhere, you can't unsee them. Look at this range: proportions, irrational numbers, polygonal numbers, perfect numbers. Each one of these is a major contribution to mathematics. Let's unpack them. Proportions. The Pythagoreans developed theories about mathematical proportions in nature and art. They discovered the golden ratio, that weird number, approximately 1.618, that shows up everywhere from nautilus shells to the Parthenon to your credit card. They believed certain proportions were inherently beautiful because they reflected cosmic harmony. And you know what? They might have been onto something. We still use these proportions in art and design because they feel right to us. But then they discovered something that absolutely shattered their worldview. Irrational numbers. Numbers that cannot be expressed as fractions, like the square root of 2. Here's the story. One of the Pythagoreans, a guy named Hippasus, was working with the theorem. He drew a square with sides of length 1. Simple, right? Then he drew the diagonal. And he asked, what's the length of that diagonal? Well, by the Pythagorean theorem, it's the square root of 2. 1 squared plus 1 squared equals the diagonal squared, so the diagonal is 2. But here's the problem. You cannot express the square root of 2 as a fraction. You cannot write it as one whole number divided by another whole number. Hippasus proved this. He showed it was impossible. And this was a disaster for Pythagorean philosophy. Because remember, they believed everything could be expressed in terms of whole numbers and their ratios. All is number, they said. But here's a number that breaks the rules. Legend says the Pythagoreans were so upset by this discovery that they took Hippasus out on a boat and drowned him. Now, I don't know if that's true. The ancient sources are unclear. But the fact that the story exists tells you how seriously they took this problem. Hey guys, I proved something mathematically rigorous that contradicts our philosophy. Cool, cool. Want to go for a boat ride? But here's what's profound. Even though irrational numbers contradicted their worldview, the Pythagoreans didn't suppress the discovery. Well, okay, maybe they drowned Hippasus, but they didn't suppress the mathematics. The proof stood. Truth won out over ideology, and they kept discovering. Polygonal numbers, number patterns that form geometric shapes. Triangular numbers, 1, 3, 6, 10, where each number represents dots that can be arranged in a triangle. Square numbers, 1, 4, 9, 16, where each forms a square. They studied these patterns obsessively, because to them, this wasn't just number theory, this was theology. These patterns revealed the divine architecture of reality. And then there are perfect numbers, numbers that equal the sum of their proper divisors. Take 6, its divisors are 1, 2, and 3. Add them up, 1 plus 2 plus 3, or 6, perfect. Or 28, its divisors are 1, 2, 4, 7, and 14. Add them, 1 plus 2 plus 4 plus 7 plus 14 more than 28. Perfect. The Pythagoreans were fascinated by these numbers. They saw them as symbols of cosmic perfection. And you know what? Perfect numbers are rare. The next one after 28 is 496, then 8128. They're incredibly hard to find. Even today, with all our computing power, we've only found about 50 perfect numbers. They remain mysterious, beautiful, strange. And yes, I know what you're thinking. Professor, this is getting pretty nerdy, even for a math lecture. But that's exactly the point. The Pythagoreans were unapologetically nerdy about mathematics. They didn't study numbers because they were useful, though they are. They studied numbers because they were beautiful, because patterns in numbers revealed patterns in reality. And here's what we need to understand. All of these contributions, the theorem, the proportions, the irrational numbers, the number patterns, they're all connected in Pythagorean thought. They believed mathematics was the language of the cosmos. Every discovery was another word in that language, another sentence in the book of nature. Some discoveries confirmed their philosophy, others challenged it, but all of them deepened their understanding. And we're still reading that book. Number theory, the study of patterns in numbers, is one of the most active areas of mathematics today. It's crucial for cryptography, for computer science, for understanding prime numbers and encryption. The Pythagoreans started this. 2,500 years ago they said, let's study numbers for their own sake, not just for practical calculation. And that decision created an entire branch of mathematics that now protects your credit card information online. But beyond the practical applications, there's something deeper here. The Pythagorean approach to mathematics, rigorous proof, pattern recognition, the search for underlying unity. This is the foundation of all scientific thinking. When we look for laws of nature, we're being Pythagorean. When we use mathematics to describe physical reality, we're being Pythagorean. When we believe the universe is comprehensible through reason, we're being Pythagorean. And they didn't stop with pure mathematics. Because once you believe mathematics describes reality, you start looking for mathematical patterns everywhere. In the movements of the planets, in the structure of music, in the nature of matter itself. So let's follow the Pythagoreans as they turn their mathematical lens toward the heavens. Alright, so the Pythagoreans have proven that mathematics describes geometric relationships. They've found patterns in numbers. And now they look up at the night sky and ask the most Pythagorean question possible. What if the heavens follow mathematical laws too? Look at these claims. Spherical Earth, mathematical orbits, harmony of the spheres. 2 of these are brilliant. 1 is beautifully wrong. Let's figure out which is which. First, the spherical Earth. Pythagoras was among the first to propose that Earth is a sphere, not a flat plane. Now, we need to be historically careful here. The idea of a spherical Earth wasn't completely unprecedented. Some earlier thinkers had speculated about it. But Pythagoras and his followers developed actual arguments for it. They didn't just guess, they reasoned. Why did they think Earth was a sphere? Several reasons. First, mathematical aesthetics. The sphere is the most perfect geometric form, so naturally the Earth should be spherical. Okay. That's not great evidence by modern standards, but stay with me. Second, and this is better. They observed that during lunar eclipses, Earth's shadow on the moon is always circular, and the only three-dimensional object that casts a circular shadow from every angle is a sphere. Third, they noticed that as you travel north or south, different stars become visible or disappear below the horizon. On a flat Earth, you'd see the same stars everywhere. On a spherical Earth, your view changes as you move across the curved surface. This is remarkable reasoning for the 6th century BC. They're using observation, geometry, and logical deduction to figure out the shape of the planet they're standing on. No satellites, no space travel, just careful thinking. And yes, I'm aware that 2,500 years later, we have people on the internet arguing that Earth is flat. Pythagoras solved this problem before Plato was born, and somehow we're still debating it. The internet was a mistake. Second claim, planets move in perfect circular motions following mathematical laws. Now here's where things get interesting. The Pythagoreans believed that celestial bodies, the sun, moon, planets, stars, all move in perfect circles at constant speeds, and they believed these movements could be described mathematically. Were they right? Yes and no. Mostly no, but in a really important way, yes. They were wrong about the circles. Planetary orbits are actually ellipses, not circles. Kepler figured that out in the 1600s, and the speeds aren't constant. Planets move faster when closer to the sun. Newton explained why. But here's what they got profoundly right. Planetary motions do follow mathematical laws. The heavens are governed by mathematics. When Newton finally worked out the laws of motion and gravity, he proved the Pythagoreans' fundamental insight. The cosmos operates according to mathematical principles. The Pythagoreans were wrong about the specific mathematics, circles versus ellipses, constant versus variable speeds. But they were right about the big idea. Mathematics describes celestial mechanics, and that insight, that the heavens follow natural laws we can discover through reason, that's the foundation of astronomy as a science. Which brings us to the third claim, the harmony of the spheres. The Pythagoreans proposed that celestial bodies create cosmic music through their movements. As the planets orbit, they produce sounds, musical tones that correspond to their speeds and distances. Together, these tones create a cosmic symphony, a music of the spheres. This is gorgeous. This is poetic. This is philosophically profound. And it's completely wrong. There is no music of the spheres. Space is a vacuum. Sound doesn't travel through vacuum. The planets orbit in silence. Sorry, Pythagoras, but hold on. Before we dismiss this as pure fantasy, let's understand what they were really saying. The Pythagoreans had discovered that musical harmony follows mathematical ratios. We'll get to that in the next slide. And they'd observed that planetary motions seem to follow mathematical patterns. So they made a logical leap. If music is mathematical and planetary motion is mathematical, maybe they're connected. Maybe the same ratios that create pleasing sounds also govern celestial movements. Were they right? Not literally, but metaphorically? Conceptually? There's something profound here. When modern astrophysicists talk about the cosmic microwave background radiation, the echo of the Big Bang, they sometimes call it the sound of the universe's birth. When they describe the oscillations of stars, they use terms like stellar harmonics. When they analyze the spacing of planetary orbits, they find mathematical relationships. The music of the spheres isn't real in the way the Pythagoreans imagined. But the idea that the cosmos has a mathematical structure, that there's an underlying harmony to physical law, that the universe is ordered rather than chaotic, that's absolutely real. And the reason the Pythagoreans believed in cosmic harmony is because they discovered something genuinely remarkable about actual music. Okay, here's where the Pythagoreans absolutely nailed it. Here's where their mathematical approach produces a discovery that's still fundamental to music 2,500 years later: string mathematics. The discovery that pleasing musical intervals correspond to simple number ratios. Let me tell you the story, because this is one of the great moments in the history of science. Legend says Pythagoras was walking past a blacksmith shop. He heard the hammers striking anvils, and he noticed something. Some combinations of hammer strikes sounded pleasant together. Others sounded harsh, discordant. Most people would just think, interesting, and move on. Pythagoras stopped and investigated. He went home and started experimenting with a monochord, a single string stretched over a soundboard. And he discovered something extraordinary. If you pluck the full string, you get a note. Let's call it C. Now, if you press down exactly halfway along the string and pluck it, you get a note exactly one octave higher, another C but higher. The ratio is 1.2. Half the string length, double the frequency, one octave up. Then he tried 2/3 of the string length. That produces a perfect fifth, the interval from C to G. The ratio is 2.3. 3/4 of the string, a perfect fourth, C to F. Ratio of 3.4. Do you see what's happening here? Musical harmony, something we experience as beautiful, as aesthetic, as emotional, is actually mathematical. The intervals that sound good to our ears are the ones with simple numerical ratios. This isn't subjective. This isn't cultural. This is physics. When you play two notes with frequencies in a 2-3 ratio, they create a perfect fifth, every time, in every culture, for every human ear. Because mathematics. This is why music is called a universal language. Not because everyone likes the same songs, we definitely don't, but because the mathematical relationships that create harmony are the same everywhere. Aliens on another planet, if they have ears and make music, would discover the same ratios produce the same intervals. The Pythagoreans identified what we now call the harmonic series, the mathematical relationships between musical notes. They discovered that consonant intervals, ones that sound good together, correspond to simple ratios, 1.2, 2, 3, 3, 4, 4.5. Dissonant intervals, ones that sound harsh, have more complex ratios, 16, 15, 45, 32, and so on. And this discovery became fundamental to Western music theory. When we talk about scales, about chords, about harmony, we're still using Pythagorean insights. His mathematical approach to harmony became the foundation of Western music theory. The major scale, based on these ratios, the circle of fifths, Pythagorean mathematics, the way we tune instruments. For centuries, we used Pythagorean tuning based on these exact ratios. Now, I should mention, and this is fascinating, Pythagorean tuning actually has problems. If you tune everything using perfect 2.3 ratios, by the time you go around the circle of fifths and come back to where you started, you're slightly off. The math doesn't quite close the loop perfectly. This is called the Pythagorean comma, and it drove music theorists crazy for centuries. Eventually, we developed equal temperament, tuning, which fudges the ratios slightly to make everything work. Your piano is tuned using equal temperament, not pure Pythagorean ratios. So even when the Pythagoreans got something brilliantly right, they got it too right. They found the mathematically perfect ratios, and then reality said, yeah, but if you use those, you can't play in all keys. Mathematics giveth, and mathematics taketh away. But here's why this matters beyond music. The Pythagorean discovery about musical ratios proved that mathematics describes not just abstract geometry, but physical phenomena. Sound waves, vibrating strings, the human perception of beauty, all following mathematical laws. Think about what we've seen in these last two slides. The Pythagoreans looked at the heavens and said, mathematics governs the cosmos. They looked at music and said, mathematics governs harmony. They were searching for a unified mathematical description of reality. When Einstein searched for a unified field theory, he was being Pythagorean. When physicists today search for a theory of everything that describes all forces through one mathematical framework, they're being Pythagorean. When we use mathematics to describe sound waves, light waves, gravitational waves, we're following the path Pythagoras started 2,500 years ago. But there's something else here, something deeply human. The Pythagoreans didn't just discover that music follows mathematical laws. They discovered that beauty and mathematics are connected. That aesthetic experience and rational understanding aren't separate realms. They're two ways of experiencing the same underlying reality. When you hear a perfect fifth and it sounds beautiful to you, you're not just having a subjective emotional response. You're perceiving mathematical truth. Your ear is detecting the 2-3 ratio. Your brain is recognizing the pattern. Beauty, in this case, is the sensory experience of mathematical harmony. And this is the Pythagorean vision at its most powerful. Mathematics isn't cold and abstract. It's the structure of reality itself. It's in the stars, in music, in the proportions of nature, in the patterns of numbers. But the Pythagoreans didn't stop with mathematics and physics. Because if numbers reveal truth about the cosmos, maybe they reveal truth about the divine. Maybe mathematics is the language God speaks. And that's where Pythagorean philosophy gets really interesting and really weird. Now we need to talk about the other side of Pythagoras, the side that makes modern scientists a little uncomfortable. Because the same man who gave us rigorous mathematical proof also believed his soul had lived in multiple bodies and that beings were dangerous. Look at these four elements: spiritual mathematics, reincarnation, sacred numbers, religious influence. This isn't a footnote to Pythagorean philosophy. This is Pythagorean philosophy, just as much as the theorem. And here's what we have to understand. For Pythagoras, there was no separation between mathematics and mysticism. They weren't doing math on Monday and religion on Tuesday. Mathematics was their religion. Numbers were their theology, spiritual mathematics. They believed mathematics revealed divine truths about reality. Think about what this means. When you prove a mathematical theorem, you're not just discovering a useful fact. You're uncovering eternal truth. You're seeing the mind of God. Mathematics exists outside of time, outside of space, outside of human culture. 2 plus 2 equaled 4 before humans existed, and it will equal 4 after we're gone. And you know what? They might have been onto something here. When mathematicians talk about their work, they often use quasi-religious language. They talk about mathematical truths as discovered rather than invented. They describe the experience of understanding a proof as almost mystical, a moment of pure clarity, of seeing eternal truth. But then there's reincarnation. Meet metempsychosis, the doctrine that souls are immortal and cycle through different bodies. Now, this wasn't a mainstream Greek belief. Most Greeks thought you died and went to Hades, end of story. But Pythagoras taught that your soul, your essential self, survives death and is reborn in another body. Maybe human, maybe animal. It depends on how you lived. There are these wonderful, bizarre stories about Pythagoras. One says he claimed to remember his past lives. He said he'd been a warrior in the Trojan War, then various other people, and he could recall specific details from each life. Another story says he once stopped someone from beating a dog because he recognized the dog's bark as the voice of a deceased friend. "Stop, that's my buddy Steve." Now, I don't know if these stories are true. They were written down centuries after his death. But they tell us something about how Pythagoras was perceived, as someone who claimed special spiritual knowledge, who saw connections between all living things. And here's where it gets philosophically serious. If souls transmigrate between bodies, then all living things are connected. The soul in that dog might have been human. The soul in you might become an animal. This led to Pythagorean vegetarianism. You shouldn't eat animals because they might contain human souls. There's something beautiful about this, right? It's an early form of universal compassion. All life is sacred. All beings deserve respect. The boundary between human and animal isn't absolute. Modern animal rights philosophy sometimes draws on similar ideas, that consciousness and the capacity to suffer matter more than species membership. And then there's the tetracties, the sacred triangle of 10. Picture a triangle made of dots. 1 dot at the top, 2 dots in the second row, 3 in the third, 4 in the fourth. Total, 10 dots. 1 plus 2 plus 3 plus 4 = 10. To the Pythagoreans, this wasn't just arithmetic. This was the structure of reality itself. 1 represented the point, the monad, unity, God. 2 represented the line, duality, the first division. 3 represented the plane, the first surface. 4 represented the solid, three-dimensional space. Together, they add to 10, the perfect number, the number that contains all geometric dimensions. The Pythagoreans swore oaths by the tetracties. They meditated on it. They saw it as a symbol of cosmic order. When they looked at this simple triangle of dots, they saw the mathematical structure of creation itself. Now, is the number 10 actually sacred? Does the tetracties reveal divine truth? Or were the Pythagoreans seeing patterns and assigning them cosmic significance because humans are really, really good at finding meaning in patterns? Probably the latter. But you know what? The search for meaningful patterns in mathematics has led to genuine discoveries. Sometimes seeing significance where others see randomness is exactly what drives breakthrough thinking. And look at the religious influence. Pythagorean ideas shaped later philosophical and religious movements. Plato absorbed Pythagorean mathematics and mysticism. His theory of forms, eternal, perfect mathematical realities that physical objects merely imitate, that's deeply Pythagorean. Neoplatonism, which influenced early Christianity, was saturated with Pythagorean number mysticism. Christian theologians used Pythagorean ideas about numerical symbolism. The Trinity as 3 in 1? Pythagorean number theology helped shape how that was understood. We need to be careful here. We're not saying Christianity is just Pythagoreanism, with Jesus added. But we are saying that Pythagorean ideas about mathematics, harmony, and the soul influence the intellectual framework through which early Christians understood their faith. And here's what fascinates me. The Pythagoreans were asking questions we're still asking. Is mathematics discovered or invented? Does it exist independently of human minds? Why does mathematics describe physical reality so perfectly? Is there something spiritual about mathematical truth? Were they right about reincarnation? I doubt it. Were they right that the number 10 is cosmically special? Probably not. That's likely just base 10 thinking from counting on fingers. But were they right that mathematics connects to something deeper than mere calculation? That understanding mathematical truth is a profound human experience? That there's something almost sacred about eternal necessary truths? Yeah, maybe they were. Okay, so we've seen the mysticism. We've seen the weird beliefs about beings and reincarnation and sacred numbers. And now I need you to see something that's easy to miss. Despite all the mysticism, the Pythagoreans developed something remarkably close to scientific method. Look at this progression. Question, hypothesis, proof, knowledge. This is systematic. This is rigorous. This is how you build reliable knowledge. Let's break this down, because this is important. First, question. Begin with precise questioning about mathematical relationships. Not vague wondering, not "I wonder what's true," but specific answerable questions. What is the relationship between the sides of a right triangle? What ratio produces a musical fifth? What shape is the earth? This is harder than it sounds. Most people ask mushy questions that can't be answered. What is the meaning of life? Why is there something rather than nothing? These are interesting, but they're not the kind of questions that lead to proof. The Pythagoreans learned to ask questions that mathematics could answer. And that discipline, learning to ask the right questions, that's half the battle in any intellectual endeavor. Second, hypothesis. Propose a mathematical principle that might explain the pattern. Notice, they didn't just observe and collect data, they proposed explanations, they made predictions. If the Earth is spherical, then we should see its circular shadow during lunar eclipses. If musical harmony follows mathematical ratios, then we should be able to predict which intervals sound consonant. This is the heart of scientific thinking. You don't just describe what you see. You propose why you see it, and your explanation has to make predictions that can be tested. Third, proof. Use deductive reasoning to establish mathematical truth. And this is where the Pythagoreans went beyond what we'd call science today and achieved something even more powerful: mathematical certainty. In science, you can never be absolutely certain. You can have overwhelming evidence, but there's always the possibility that the next experiment will contradict your theory. That's the nature of empirical investigation. But in mathematics, with rigorous proof, you can be certain, absolutely, eternally certain. When Pythagoras proved his theorem, he didn't prove it's probably true, or true as far as we can tell. He proved it's necessarily true. It cannot be otherwise. In all possible worlds, in all possible universes, A2 plus B2 ought C2 for right triangles. Now here's the trade-off. Mathematical proof only works for mathematical truths. You can't prove the Earth is spherical with pure deduction. You need observation. You can't prove that musical intervals follow ratios without actually listening to them. But what you can do is use mathematics to describe what you observe. You can prove that, if the certain observations are accurate, then certain conclusions must follow. And this is what the Pythagoreans pioneered: the combination of empirical observation and mathematical reasoning. They observed the shadow during lunar eclipses, then used geometry to prove what shape must cast that shadow. They listened to musical intervals, then used mathematics to prove what ratios produce them. They measured triangles, then proved the relationship must hold for all triangles. Fourth, knowledge. Share verified principles as foundations for further exploration. And this is crucial. Knowledge isn't private. Once you've proven something, you share it. It becomes part of the collective understanding. Other people can build on it, test it, extend it. This is why the Pythagorean school was so important. Yes, they had their secrecy and their inner circles, but within the community, knowledge was shared. Students built on teachers' work. Discoveries were preserved, transmitted, refined. This is the beginning of science as a collective human enterprise, not individual geniuses working in isolation, but a community of scholars building knowledge together. Although, let's be honest, there's a delicious irony here. The Pythagoreans developed a systematic method for discovering truth, but they also believed in sacred numbers and reincarnation and the music of the spheres. They had rigorous standards for mathematical proof, but they also thought beings were spiritually dangerous. And here's what we need to understand. This isn't hypocrisy. This is what intellectual progress actually looks like. You don't go from complete ignorance to perfect scientific method in one generation. You develop rigorous thinking in some areas while maintaining traditional beliefs in others. You're brilliant about mathematics while being wrong about astronomy. You pioneer logical proof while believing in mysticism. The Pythagoreans were humans, not logic machines. They were trying to understand reality with the tools they had. And the tools they developed, precise questioning, mathematical reasoning, deductive proof, shared knowledge, those tools were revolutionary, even if they didn't apply them consistently to everything. What they gave us is a method, a way of approaching questions that produces reliable knowledge. Not perfect knowledge, not complete knowledge, but knowledge that builds, that accumulates, that gets us closer to truth. When modern scientists formulate hypotheses and test them, they're using a more sophisticated version of the Pythagorean approach. When mathematicians prove theorems, they're following the path Pythagoras laid out. When we insist on evidence and logical reasoning, we're being Pythagorean. And here's what amazes me. 2,500 years later, we're still using this method. We've refined it, extended it, applied it to areas the Pythagoreans never imagined. But the basic approach, ask precise questions, propose explanations, prove them rigorously, share the results, that's still how we build knowledge. But having a good method doesn't guarantee success, and having brilliant ideas doesn't protect you from political backlash. The Pythagoreans were about to learn this the hard way. Now we need to talk about power. Because the Pythagoreans weren't just sitting around doing geometry and meditating on sacred numbers. They were running cities. Look at these numbers. Over 300 followers in the inner circle in Croton alone. Political offices held in 5 major Greek colonies. 50-plus years of Pythagorean political influence across Magna Graecia, that's southern Italy and Sicily. This isn't a philosophy club. This is a political movement. For half a century, Pythagorean ideas shaped how cities were governed across the Greek world. So what did Pythagorean politics look like? Well, remember their core belief. The universe operates according to mathematical harmony. Everything has its proper proportion, its correct relationship to everything else. They applied this to politics. They believed society should be organized according to rational principles, with each person in their proper role, creating social harmony the way musical notes create acoustic harmony. And you can see why this was attractive, right? In an age of tyrants and chaos, here's a philosophy that promises order based on reason rather than force. Here's a vision of society as a harmonious whole rather than a power struggle. The Pythagoreans offered something seductive. Philosopher kings. Rule by the wise. Government based on mathematical principles of justice and proportion. It's the dream of every intellectual. What if smart people ran things? What if we made decisions based on reason rather than passion, on knowledge rather than ignorance? Spoiler alert, it doesn't work out the way you'd hope. Because here's the thing, and we need to be honest about this. Pythagorean politics was fundamentally aristocratic. They believed in rule by the educated elite. The mathematikoi, the inner circle who understood the deeper teachings they should govern. The masses who didn't understand mathematical truth should follow. And in Croton and other cities, this is exactly what happened. Pythagoreans held key political offices. They influenced laws, shaped policy, controlled resources. They formed what we might call today an intellectual oligarchy. Now imagine you're a regular citizen of Croton. You're not part of this exclusive brotherhood. You don't know their secret teachings. You're not invited to their communal dinners or their philosophical discussions. But these people are making decisions that affect your life. They're passing laws you have to follow. They're using their network to gain political advantage, and when you ask them to explain their reasoning, they say, "You wouldn't understand." It's based on mathematical principles we can't share with outsiders. How long before you start thinking, This is tyranny with a philosophical veneer, and this is a pattern we see throughout history. Intellectuals gain political power, convinced their superior knowledge justifies their authority. They create exclusive systems. They become disconnected from the people they govern, and eventually there's a backlash. In the Pythagorean case, there were specific complaints. They were accused of forming a secret society that put loyalty to the brotherhood above loyalty to the city. They were accused of using their network for mutual advantage. They were accused of being anti-democratic, of believing the masses couldn't be trusted with self-governance. Were these accusations fair? Probably some of them. The Pythagoreans did form an exclusive society. They did believe in rule by the educated. They did maintain secrets and create an inner circle. But were they corrupt? Were they tyrannical? The historical record is unclear. What we know is that their opponents believed they were, and that was enough. So, by around 510 BC, you've got this situation. The Pythagoreans are powerful, influential, and increasingly resented. Democratic factions are organizing against them. Tensions are rising, and it's about to explode. What happens next is violent, tragic, and ultimately transforms Pythagorean philosophy from a political movement into something else entirely. Around 510 BC, the backlash comes, and it comes hard. Political backlash, forced exile, death, scattered followers. This is the end of the Pythagorean political experiment. But as we'll see, it's not the end of Pythagorean ideas. Democratic factions attacked Pythagorean meeting places. And we're not talking about protests or political opposition. We're talking about violence, buildings burned, people killed. The ancient sources give us different versions of what happened. Some say a man named Cylon, who'd been rejected from the Pythagorean Brotherhood, led a mob against them. Others say it was a broader democratic uprising. The details vary, but the outcome is consistent. The Pythagorean community in Croton was destroyed. Picture it. The meeting house is surrounded. Maybe there's a lecture happening, or a communal meal. Suddenly there's shouting, torches, a mob. The Pythagoreans are trapped inside. The building is set on fire. Some sources say dozens died in that fire. Others say hundreds. We don't know the exact number, but we know this. A community that had existed for decades, that had produced mathematical discoveries and philosophical insights, that had shaped the politics of an entire region. It was destroyed in a single night of violence. And Pythagoras himself? He fled. He was probably in his 70s by this point, an old man watching his life's work burn. He eventually settled in Metapontum, another Greek colony in southern Italy, and there, around 495 BC, he died. The circumstances of his death are unclear. Some sources say he died peacefully, others say he was hunted down by his enemies. One particularly dramatic account says he was fleeing pursuers and came to a field of beans, and rather than cross it, remember, beans were forbidden, he stopped and was killed. I don't know if that story is true, but if it is, there's something both tragic and absurd about it. The man who discovered eternal mathematical truths, killed because he wouldn't walk through a bean field. It's the kind of detail that makes you wonder if the universe has a sense of humor. But the real story isn't Pythagoras' death. The real story is what happened to his followers. Surviving Pythagoreans dispersed throughout the Greek world. They went to Athens, to Egypt, to Sicily, to mainland Greece. They carried their knowledge with them, the mathematical discoveries, the philosophical teachings, the methods of inquiry. And here's what's remarkable. The destruction of the Pythagorean political community actually helped spread Pythagorean ideas. When they were concentrated in Croton, they were powerful but isolated. When they scattered, they became teachers, influencers, transmitters of knowledge across the entire Mediterranean world. Some went to Athens and influenced Plato. Some preserved the mathematical discoveries in written form. Some continued teaching, creating new schools, adapting Pythagorean philosophy to new contexts. The political movement died. The exclusive brotherhood was broken. But the ideas, the mathematics, the philosophy, the methods, they survived. And there's something profound here about the nature of intellectual work. You can burn buildings, you can kill people, you can destroy communities, but you cannot destroy ideas. The Pythagorean theorem doesn't care that the Pythagorean school was destroyed. Mathematical proof doesn't depend on political power. Truth survives the death of those who discover it. In fact, the persecution might have helped. When you're a powerful political faction, people resist your ideas because they resist your power. But when you're scattered refugees, when you're teachers rather than rulers, people are more willing to listen. Pythagoras learned, though he didn't live to fully appreciate it, that philosophy and political power don't mix well. When philosophers try to rule, they become politicians. And when politicians claim philosophical authority, they become tyrants. It's the problem Plato would grapple with in The Republic. How do you get philosopher kings without the king's part corrupting the philosopher part? Spoiler, you probably can't. But here's what the fall of the Pythagorean school teaches us. Ideas are more durable than institutions. Methods are more powerful than movements. Truth outlasts the people who discover it. The Pythagoreans as a political force lasted maybe 50 years. The Pythagoreans as an intellectual tradition, they're still with us 2,500 years later. And in the centuries after Pythagoras' death, his ideas would spread further than he could have imagined. They would influence Plato, Aristotle, Euclid. They would shape mathematics, philosophy, science, music theory. The scattered Pythagoreans became something new. Not a political movement, not an exclusive brotherhood, but a philosophical tradition. Anyone could study Pythagorean mathematics. Anyone could read about Pythagorean ideas. The secrets became public knowledge. And in a way, this was the ultimate triumph of Pythagorean philosophy. Because remember their core belief, mathematics reveals universal truth. Truth that doesn't depend on who you are, where you're from, what political faction you belong to. Well, when the political faction was destroyed, the universal truth remained. And it spread precisely because it was universal, because it was true, because anyone with reason could understand it. Pythagoras died in exile, his school destroyed, his political dreams in ruins, but his mathematics lived on, his methods endured. His vision of a rational, mathematically ordered universe became the foundation of Western science. So the question becomes, what exactly did survive? What did the scattered Pythagoreans carry with them? What did they teach to Plato and the philosophers who came after? Let's trace that legacy. Alright, so the Pythagorean school is destroyed, the brotherhood is scattered, Pythagoras is dead. And you might think that's the end of the story. But here's where it gets interesting. Because the two most important philosophers in Western history, Plato and Aristotle, they're both completely obsessed with Pythagoras. Look at this. Platonic influence, Aristotelian analysis, continued schools. The Pythagorean legacy flows through multiple channels, transforming as it goes. Let's start with Plato. When Plato writes his dialogues in the 4th century BC, about 100 years after Pythagoras' death, he's working in a world saturated with Pythagorean ideas. And Plato doesn't just reference Pythagoreanism, he absorbs it. He makes it central to his entire philosophical system. Think about Plato's theory of forms, his most famous idea. He says there's a realm of perfect, eternal, unchanging forms. The physical world is just a pale imitation of these perfect realities. A triangle you draw is imperfect, but the form of triangle is perfect and eternal. Where does this come from? Pythagoras. The idea that mathematical truths are eternal, perfect, and more real than physical objects, that's pure Pythagoreanism. Plato believed the universe was constructed according to mathematical principles. In the Timaeus, he describes the creator, the demiurge, building the cosmos using geometric shapes. The elements are made of regular solids. Fire is tetrahedrons, earth is cubes, air is octahedrons, water is icosahedrons. This is Pythagorean mysticism combined with Pythagorean mathematics. The idea that reality is fundamentally mathematical, that geometry reveals the structure of the cosmos, Plato got this from the Pythagorean tradition. And look at Plato's academy, the school he founded in Athens. What did students study? Mathematics. Lots of mathematics. Geometry, arithmetic, astronomy, music theory. There's a famous story, probably apocryphal but revealing, that above the entrance to Plato's academy was written, "Let no one ignorant of geometry enter here." Plato basically said, you want to do philosophy? First, learn math. Which, if you think about it, is exactly what Pythagoras required. The acousmatikoi had to master the basics before they could access the deeper teachings. Plato is running a Pythagorean school, he's just not calling it that. But Plato also incorporated Pythagorean mysticism. The immortality of the soul? Pythagorean. The idea that the soul existed before birth and will exist after death? Pythagorean. The notion that philosophical contemplation purifies the soul? Pythagorean. Now Plato isn't just copying Pythagoras, he's transforming these ideas, developing them, making them his own. But the foundation is Pythagorean. Without Pythagoras, there's no Plato as we know him. And then there's Aristotle, Plato's student, but a very different kind of thinker. Aristotle documented and critiqued Pythagorean ideas in his writings. And this is crucial because much of what we know about early Pythagoreanism comes from Aristotle. Here's the irony. Aristotle disagreed with a lot of Pythagorean philosophy. He thought their number mysticism was confused. He rejected the idea that everything is literally made of numbers. He was skeptical of their cosmology. But because he took them seriously enough to argue against them, he preserved their ideas. He wrote things like, "The Pythagoreans say that," and then explained their position before critiquing it. Without Aristotle, we'd know far less about what the early Pythagoreans actually believed. The Pythagoreans themselves wrote very little that survived. Remember, they were secretive, and much of their teaching was oral. But Aristotle, in his careful, systematic way, documented their doctrines. Even while disagreeing with them, he showed them respect as serious thinkers worthy of philosophical engagement. And in a way, this is the beginning of academic tradition as we know it. You don't just present your own ideas. You engage with previous thinkers. You cite them, explain them, critique them. You build on what came before even when you're arguing against it. Aristotle is writing the first literature review, and the Pythagoreans are prominently featured. But here's what's really remarkable. Pythagorean communities persisted for centuries after Pythagoras' death. Not the original brotherhood in Croton. That was destroyed. But new Pythagorean schools, scattered across the Greek world, continued teaching Pythagorean mathematics and philosophy. These later Pythagorean schools were different from the original. They were less secretive, less politically involved, more focused on mathematics and philosophy than on communal living and dietary restrictions. But they preserved the core insights. Mathematics reveals truth. The universe operates according to rational principles. Philosophical contemplation elevates the soul, and these schools produced important thinkers. Archytas of Tarentum, in the 4th century BC, was a brilliant mathematician and a friend of Plato. Philolaus wrote one of the first books explaining Pythagorean philosophy, and Plato probably read it. The tradition evolved, adapted, survived, not as a political movement, but as an intellectual lineage. And this tells us something important about how ideas spread and endure. The original Pythagorean community, exclusive, secretive, politically powerful, that couldn't last. It was too rigid, too threatening, too dependent on charismatic leadership. But the ideas, once they escaped the confines of the original community, once they were written down and taught openly, those could spread, evolve, influence other thinkers. So by the time we get to the end of the classical period, Pythagoreanism isn't one thing. It's a strand running through Platonic philosophy. It's a set of mathematical discoveries preserved in textbooks. It's a mystical tradition about the soul and reincarnation. It's a method of inquiry based on mathematical reasoning. And all of these different versions of Pythagoreanism, they're about to have an even bigger impact. Because the ideas that influence Plato and Aristotle are going to influence everyone who comes after them. Now let's talk about the really long-term legacy. Because Pythagorean concepts didn't just influence ancient philosophy. They form the cornerstone of mathematics as we know it. Pythagorean concepts form the cornerstone of mathematics. From Euclid's geometry to modern number theory, his approach remains relevant. And I need you to understand, this isn't exaggeration. This isn't giving Pythagoras credit for things he didn't do. This is recognizing that the way we do mathematics today, the entire structure of mathematical thinking, has Pythagorean DNA. Let's start with Euclid. Around 300 BC, Euclid writes, "The Elements," the most influential mathematics textbook ever written. For 2,000 years, this is how people learned geometry. And what's in it? Pythagorean mathematics. The Pythagorean theorem is proposition 47 in Book 1 of the Elements. Euclid gives a complete proof, not the same proof Pythagoras used, but a rigorous demonstration that the relationship holds. But it's not just the theorem. The entire approach, start with definitions and axioms, build up through logical proofs, establish theorems with certainty, that's the Pythagorean method formalized. And this is what I want you to see. The specific discoveries matter. The Pythagorean theorem is important, but the method, that's what changes everything. Before Pythagoras, mathematics was practical. You measured fields, calculated taxes, built buildings. You had rules of thumb that worked. After Pythagoras, mathematics became a system of proven truths. You didn't just know that something worked, you knew why it worked, and you could prove it must always work. And this approach, this insistence on proof, on logical rigor, on mathematical certainty, it continues right through to modern mathematics. When a modern mathematician proves a theorem, they're following the Pythagorean tradition. When they build complex proofs from simpler axioms, they're being Pythagorean. When they insist that mathematical truth is eternal and necessary, they're echoing Pythagoras. And look at number theory, the study of patterns in numbers. This is one of the most active areas of mathematics today. It's crucial for cryptography, for computer science, for understanding prime numbers. Where did it start? With the Pythagoreans studying perfect numbers, triangular numbers, the properties of odds and evens. Here's what's funny. The Pythagoreans studied number patterns because they thought numbers were sacred, because they were looking for cosmic significance, because they believed in number mysticism. And 2,500 years later, we're studying the same patterns because we need to encrypt your credit card information online. They were doing it for God. We're doing it for Amazon. But the mathematics is the same. But there's something more profound here than just we still use their discoveries. There's a philosophical continuity. Remember the core Pythagorean insight. Mathematics describes reality, not just approximately, not just as a useful tool, but fundamentally. The universe operates according to mathematical laws. Every time a physicist writes an equation describing how particles interact, they're affirming the Pythagorean vision. Every time an astronomer uses mathematics to predict planetary positions, they're being Pythagorean. Every time an engineer uses geometry to design a structure, they're working in the Pythagorean tradition. And in modern physics, this Pythagorean vision has been vindicated in ways that would have amazed Pythagoras himself. Quantum mechanics? Described by mathematics. Relativity? Mathematical equations. The standard model of particle physics? Pure mathematics. There's a famous essay by physicist Eugene Wigner called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He asks, why does mathematics work so well for describing physical reality? Why should abstract mathematical structures correspond so perfectly to the way the universe actually operates? This is the Pythagorean question, and we still don't have a complete answer. Is mathematics discovered or invented? Does it exist independently of human minds? Why does the universe seem to be written in mathematical language? Pythagoras asked these questions 2,500 years ago. We're still asking them. Now, we need to be clear. Pythagoras got a lot of things wrong. The music of the spheres? Wrong. Planets moving in perfect circles? Wrong. Everything being literally made of numbers? Wrong, or at least not in the way he thought. But the method, using mathematics to understand nature, insisting on proof, looking for underlying patterns and principles, that was profoundly right, and that's what endures. Not the specific theories, but the approach. Not the mysticism, but the mathematics. Not the cult, but the method. From Euclid's geometry to modern number theory, the Pythagorean approach remains relevant. And by relevant, I don't mean historically interesting. I mean actively used, currently essential, foundational to how we think. Every mathematics student who learns to write proofs is inheriting the Pythagorean tradition. Every scientist who uses mathematics to describe natural phenomena is working in the framework Pythagoras established. Every philosopher who thinks about the relationship between mathematics and reality is grappling with Pythagorean questions. This isn't ancient history. This is the intellectual infrastructure of modern civilization. When you use GPS and it calculates your position using the Pythagorean theorem, that's not just a practical application. That's a 2,500-year-old idea, proven with ancient Greek logic, implemented in modern technology. When you listen to music and hear harmony, you're experiencing the mathematical ratios the Pythagoreans discovered. When you study geometry in school, you're learning theorems they proved. When you use encryption online, you're relying on number theory they pioneered. And this is what's remarkable about mathematics. Political movements rise and fall, empires come and go, cultures transform, but mathematical truth endures. The Pythagorean theorem was true before Pythagoras proved it. It was true when the Pythagorean school was destroyed. It was true through the fall of Rome, the Middle Ages, the Renaissance, the modern era. It will be true after our civilization is gone. So yes, Pythagoras died in exile. His school was burned. His political movement failed. His mystical beliefs were largely abandoned. But his mathematics, his method, his vision of a rational, mathematically ordered universe, those conquered the world. Not through force, not through political power, but through truth. Through the simple fact that they worked, that they were right, that they revealed something real about the structure of reality. And that legacy, that influence on how we think, how we do science, how we understand the universe, that's what we need to explore next. Because Pythagoreanism didn't just influence mathematics. It shaped Western philosophy, science, even religion. Now we need to step back and see the full scope of Pythagorean influence. Because this isn't just about mathematics or even science. This is about how Western civilization thinks about reality itself. Look at these: mathematical universe, Neoplatonism, Christian thought, Renaissance revival. Each one represents a major current in Western intellectual history, and all of them flow from Pythagorean sources. Let's start with the big one, the mathematical universe. The revolutionary concept that nature follows mathematical principles. This is so fundamental to how we think today that we forget it's not obvious. It's not self-evident. It's a philosophical claim that had to be discovered, argued for, proven. Think about what Pythagoras was claiming. The universe isn't chaos. It isn't controlled by capricious gods doing whatever they want. It isn't fundamentally mysterious and unknowable. Instead, reality has a structure. That structure is mathematical, and human reason can discover it. This changes everything. If the universe follows mathematical laws, then you can predict the future, at least the physical future. You can calculate when eclipses will happen, where planets will be, how objects will move. You can understand causes. Why does this happen? Because it follows from these mathematical principles. You can manipulate nature. If you understand the laws, you can use them. Engineering becomes possible. Technology becomes possible. This is the intellectual foundation of science. Not the methods, those came later, but the basic assumption that makes science possible. Nature is rational, orderly, and comprehensible through mathematics. And this Pythagorean assumption became central to Western thought. When Galileo said, "The book of nature is written in the language of mathematics," he was being Pythagorean. When Newton formulated laws of motion and gravity, he was fulfilling the Pythagorean vision. When Einstein sought a unified field theory, he was pursuing the Pythagorean dream. This is a 2,500-year-old conversation, and we're still having it. When physicists search for a theory of everything, they're asking the Pythagorean question, what's the underlying mathematical structure that explains all of reality? Now the second pathway, Neoplatonism. This is where Pythagorean mysticism gets incorporated into a major philosophical movement. In the 3rd century AD, a philosopher named Plotinus creates what we call Neoplatonism. It's a synthesis of Plato's philosophy with other traditions, and it's saturated with Pythagorean ideas. Plotinus talks about the One, the ultimate reality from which everything emanates. And how does he describe it? Using Pythagorean number symbolism. The One is beyond being, beyond thought, the source of all multiplicity. From the One comes the intellect, the realm of forms, very Platonic, very Pythagorean. From the intellect comes the soul. From the soul comes the material world. And this hierarchy is understood mathematically. Unity divides into multiplicity. The simple becomes complex. The eternal generates the temporal, all following rational mathematical principles. And Neoplatonism becomes hugely influential. It shapes late Roman philosophy. It influences early Christian theology. It gets revived in the Renaissance. It affects Islamic philosophy. And running through all of it is this Pythagorean thread. Reality has a mathematical structure. Numbers aren't just counting tools, they reveal the nature of being itself. Which brings us to the third pathway, Christian thought. Now this is fascinating and complex. Early Christian thinkers incorporated Pythagorean numerical symbolism into their theology. Think about the Trinity, three persons in one God. Christian theologians used Pythagorean ideas about the number 3 to explain this mystery. 3 is the first number that creates a surface, a plane. 3 is completion, perfection. Or the number 7, the days of creation, the number of perfection. This is Pythagorean number mysticism adapted for Christian purposes. Which is kind of ironic, right? The Pythagoreans were pagans. They believed in reincarnation, which Christianity explicitly rejects. They worshipped numbers as divine. But Christian theologians said, you know what? The number symbolism is actually pretty useful. We'll take that part, thanks. Augustine, one of the most influential Christian theologians, was deeply influenced by Neoplatonism, which means indirectly by Pythagoreanism. His ideas about eternal truths, about mathematics as a window into divine mind, about the rational order of creation, these all have Pythagorean roots. And through the Middle Ages, this continues. Medieval scholars studied the quadrivium, arithmetic, geometry, music, astronomy, the four mathematical arts. Why? Because they believed mathematics revealed divine truth. This is Pythagorean education, Christianized and formalized. And then, the fourth pathway, the Renaissance revival. In the 15th and 16th centuries, European scholars rediscovered ancient Greek texts, and they became obsessed with Pythagoras. Copernicus, who proposed that Earth orbits the Sun, was explicitly inspired by Pythagorean ideas. The Pythagoreans had suggested that Earth moves, not in the way Copernicus described, but the basic idea that Earth isn't the stationary center of the universe. Kepler, who discovered that planetary orbits are ellipses, was trying to find the mathematical harmonies in the heavens. He was pursuing the Pythagorean dream of cosmic harmony. He even wrote a book called Harmonicas Mundi, the harmony of the world. And this Renaissance revival of Pythagorean mathematical approaches helped spark the scientific revolution. The idea that you could understand nature through mathematics, that the universe followed rational laws, this became the foundation of modern science. So here's the arc. Pythagoras proposes that mathematics describes reality. This idea influences Plato. Plato influences Aristotle and the entire Greek philosophical tradition. That tradition gets preserved, transmitted, transformed through Neoplatonism and Christian theology. Then it gets revived in the Renaissance and becomes the foundation of modern science. And we're still grappling with the questions Pythagoras raised. Why does mathematics work so well for describing nature? Is mathematical truth discovered or invented? What's the relationship between abstract mathematical structures and physical reality? Is the universe fundamentally mathematical, or do we just use mathematics as a tool to describe it? These aren't historical curiosities, these are active philosophical debates. When physicists argue about whether mathematics is unreasonably effective, in describing nature, they're continuing a conversation Pythagoras started. But Pythagoras' influence isn't just in philosophy and science. He's also become a cultural icon, a symbol, a figure in popular imagination. Alright, so we've talked about Pythagoras the mathematician, Pythagoras the philosopher, Pythagoras the mystic, Pythagoras the political leader. Now let's talk about Pythagoras the brand. Classical art, educational icon, digital media, from Renaissance paintings to high school textbooks to video games. Pythagoras is everywhere. Let's start with classical art. In the Renaissance, when artists wanted to portray the ideal of wisdom, learning, and mathematical genius, who did they paint? Pythagoras. The most famous example is Raphael's School of Athens, painted in the Vatican in 1509-1511. It's this massive fresco showing all the great ancient philosophers gathered together. And there's Pythagoras in the foreground, writing in a book surrounded by students. He's portrayed as the archetypal mathematician philosopher, wise, dignified, teaching the next generation. Never mind that Pythagoras probably never met most of these other philosophers. Never mind that he lived centuries before some of them. This is Renaissance fan fiction. What if all the smart ancient Greeks hung out together? Wouldn't that be cool? But the point isn't historical accuracy. The point is what Pythagoras represents, the union of mathematics and philosophy, the idea that rational inquiry leads to wisdom, the teacher who transforms students through knowledge. And this brings us to the second category, educational icon. Pythagoras is featured in countless textbooks as a symbol of mathematical discovery. And I mean countless. Every geometry textbook has his theorem. Many have his portrait, or at least what Renaissance artists imagined he looked like, since we have no idea what he actually looked like. And there's something interesting about this. When students learn the Pythagorean theorem, they're not just learning a formula, they're being introduced to a person, a story, a tradition. This theorem is named after Pythagoras, an ancient Greek mathematician who lived 2,500 years ago. Suddenly, mathematics isn't just abstract symbols. It's human. It has history. Someone discovered this, someone proved it, someone thought it was important enough to teach others. Now, there's a problem with this. By focusing on Pythagoras the individual, we sometimes obscure the collective nature of mathematical discovery. The Pythagorean theorem wasn't just Pythagoras, it was the Pythagorean school, the community of scholars working together. And we know elements of the theorem were known before Pythagoras. So why is it named after him? Partly because Pythagorean theorem sounds better than the theorem that was known in Babylon and Egypt, but first rigorously proved by some guy in ancient Greece whose name we're not entirely sure of theorem. Branding matters, even in mathematics, but there's value in having these iconic figures. Pythagoras becomes a symbol of what's possible, a reminder that individuals can make discoveries that last millennia, an inspiration for students. If Pythagoras could figure this out 2,500 years ago, you can understand it today. And now the third category, digital media. Pythagoras appears in modern video games, films, and novels as a symbol of wisdom. This is where it gets really interesting because now Pythagoras is being reimagined for contemporary audiences who may know nothing about ancient Greek philosophy. In video games, Pythagoras often appears as the wise old mentor character, the one who gives you mathematical puzzles to solve, the one who explains the mystical significance of numbers, the one who teaches you the secrets of the universe. In Assassin's Creed Odyssey, which is set in ancient Greece, you can meet Pythagoras, and he's portrayed as this mystical figure who's lived for centuries through some kind of ancient technology, because of course he has. The game takes the historical Pythagoras, adds the legendary Pythagoras, throws in some science fiction, and creates this character who's part mathematician, part mystic, part immortal sage. Is it historically accurate? Absolutely not. Is it fun? Apparently, yes. But here's what's interesting. Even in these fictionalized versions, Pythagoras represents something consistent. Wisdom through mathematics, hidden knowledge, the idea that understanding numbers unlocks deeper truths. The specific details change. He's not teaching reincarnation in video games, he's not running a commune. But the core symbolism remains. Pythagoras equals mathematical wisdom. In novels, Pythagoras appears as a character in historical fiction, as a reference point in mathematical thrillers, as a symbol in philosophical works. There are books about the Pythagorean theorem, books about Pythagorean philosophy, books that use Pythagorean ideas as plot devices. And yes, there are conspiracy theories. What if Pythagoras discovered ancient alien mathematics? What if the Pythagorean Brotherhood was hiding secret knowledge that could change the world? The internet has taken a 6th century BC Greek mathematician and turned him into a character in the X-Files. But what does all this cultural presence reveal? Why does Pythagoras persist in popular imagination? I think it's because he represents an archetype we find compelling. The wise teacher who understands hidden patterns. The person who sees connections others miss. The one who can explain the mysterious through mathematics. In a world that often feels chaotic and incomprehensible, Pythagoras symbolizes the possibility of understanding. The idea that there are patterns, that there are laws, that reality makes sense if you just know the right mathematics. And this is how legacy works. The historical Pythagoras, the actual person who lived in the 6th century BC, he's lost to us. We don't know what he really looked like, what his voice sounded like, what he was like as a person. But the symbolic Pythagoras, the cultural icon, the representation of mathematical wisdom, he's alive and well. He's in textbooks, in art, in games, in novels. And in a way, there are multiple Pythagorases. There's the historical Pythagoras, what we can actually verify about the man who lived. There's the legendary Pythagoras, the stories, myths, and exaggerations that grew up around him. There's the mathematical Pythagoras, the theorem and discoveries attributed to him. There's the philosophical Pythagoras, the ideas and methods that bear his name, and there's the cultural Pythagoras, the symbol, the icon, the character in our collective imagination. And here's the thing, they're all real. They're all part of his legacy. The historical person influenced the legend. The legend influenced how people understood the mathematics. The mathematics influenced the philosophy. And all of it together created the cultural icon. So when a student in a classroom today learns the Pythagorean theorem, they're connecting to all of these Pythagorases. The historical mathematician who first proved it, the legendary sage who supposedly sacrificed oxen in celebration, the philosophical tradition that saw mathematics as sacred, the cultural symbol of wisdom and learning. Pythagoras wanted to achieve immortality through reincarnation. He believed souls cycle through different bodies forever. Did he achieve immortality? Well, not through reincarnation, but through ideas, through cultural memory, through the fact that 2,500 years later, millions of people know his name and use his discoveries? Yeah, he kind of did. And this raises profound questions about legacy, about what survives, about what matters. Pythagoras' political movement failed. His mystical beliefs were largely abandoned. His specific theories about the cosmos were proven wrong. But his mathematics endures. His methods persist. His name is known. His ideas continue to influence how we think. Is that success? Is that what matters? Not political power, not being right about everything, but contributing ideas that outlast you, that shape how future generations understand reality? I think Pythagoras would say yes, because for all his mysticism, for all his belief in reincarnation and sacred numbers, he understood something profound. Ideas are immortal. Truth is eternal. All right, we need to have an honest conversation. Mathematics lasts forever, because I've been telling you this story about Pythagoras for the last hour, and now I need to tell you something uncomfortable. We don't actually know how much of it is true. Look at these. Attribution problems, historical accuracy, Eastern influences. Each one represents a fundamental uncertainty about what we think we know. And this isn't me being wishy-washy. This is what intellectual honesty looks like. When you study ancient history, especially someone who lived 2,500 years ago, you have to grapple with the fact that our sources are incomplete, contradictory, and often written centuries after the events they describe. Let's start with the big one. Attribution problems. Scholars debate which discoveries were truly made by Pythagoras himself. Here's the problem. The Pythagorean school existed for generations. Hundreds of people working together, making discoveries, and they had this practice of attributing everything to Pythagoras, the founder. So when we say Pythagoras discovered X, what we often mean is someone in the Pythagorean school discovered X and they credited it to Pythagoras because that's what they did. Think about it like this. Imagine if every scientific discovery at MIT was attributed to the founder of MIT. Every paper, every breakthrough, every innovation, all credited to William Barton Rogers, even though he died in 1882. That would be weird, right? But that's essentially what the Pythagoreans did. It was a mark of respect, a way of honoring the tradition, but it makes it really hard for historians to figure out who actually did what. Did Pythagoras himself prove the Pythagorean theorem? Maybe. Probably. But we're not certain. Did he discover the mathematical ratios in music? The tradition says yes, but some scholars think this might have been discovered by later Pythagoreans. Did he propose that Earth is spherical? Possibly, but this might have been Parmenides or another early Greek thinker. It's like trying to figure out who wrote which Beatles song if all you had were accounts written 200 years after the band broke up and everyone just said the Beatles wrote it, without specifying whether it was John, Paul, George, or Ringo. Does this uncertainty diminish Pythagoras' importance? No, because even if we can't attribute every specific discovery to him personally, we know the Pythagorean school existed. We know they made these discoveries. We know Pythagoras founded the school and established its methods. And there's an argument that the founder deserves credit for creating the environment where discoveries happen. Steve Jobs didn't personally design every component of the iPhone, but we still talk about Jobs' iPhone because he created the vision and the organization that made it possible. Maybe that's how we should think about Pythagoras. Even if he didn't personally prove every theorem, he created the intellectual community that did. Now, historical accuracy. No surviving texts written by Pythagoras exist today. Let me be clear about what this means. Everything we know about Pythagoras comes from other people writing about him. And most of those people were writing centuries after he died. The earliest substantial accounts we have are from Plato and Aristotle, writing 150 years after Pythagoras' death. That's like us writing a biography of someone from the 1870s based on oral tradition and scattered references. And then we have later biographies, Diogenes Laertius, Iamblichus, Porphyry, written 700, 800 years after Pythagoras died. These are full of miraculous stories, legends, obvious exaggerations. They say Pythagoras had a golden thigh, that he could be in two places at once, that he remembered all his past lives, that he could talk to animals. These are the ancient equivalent of 10 amazing facts about Pythagoras you won't believe. Number 7 will shock you, and number 7 is probably, he had a golden thigh. So how do we separate fact from legend? Carefully, skeptically, by comparing sources, looking for consistency, applying historical reasoning. We're pretty confident Pythagoras existed, founded a school, influenced Greek mathematics and philosophy. We're less confident about specific biographical details, miraculous claims, or exact chronology. And this is what good historical thinking looks like. You don't just accept everything you read. You don't dismiss everything as myth. You carefully evaluate sources, acknowledge uncertainty, and build the most plausible account you can from incomplete evidence. And then there's the debate about Eastern influences. How much Pythagorean thought derived from Eastern traditions? Remember, Pythagoras traveled to Egypt and Babylon. He studied with priests and scholars there. So the question is, how much of what we call Pythagorean philosophy is actually Egyptian or Babylonian philosophy that Pythagoras learned and brought back to Greece? And this is a really important question, because for a long time, Western intellectual history was told as if the Greeks invented everything ex nihilo, as if philosophy and mathematics just spontaneously appeared in Greece with no outside influence. That's obviously wrong. The Greeks were part of a broader Mediterranean world. They traded with, learned from, and were influenced by other cultures. We know the Babylonians had sophisticated mathematics. They knew Pythagorean triples, sets of numbers that work in the Pythagorean theorem, centuries before Pythagoras. We know the Egyptians used geometry for surveying and construction. They had practical mathematical knowledge. So did Pythagoras discover these things, or did he learn them from Eastern sources and systematize them? Probably both. He probably learned a lot from Eastern traditions, but he also transformed what he learned. He turned practical mathematics into theoretical mathematics. He turned numerical patterns into philosophical principles. He added the element of rigorous proof. And maybe that's his real contribution. Not discovering everything from scratch, but synthesizing diverse traditions, adding the element of proof, and creating a systematic approach to mathematics and philosophy. That's still hugely important, even if it's not pure Greek invention. There's this weird anxiety in Western intellectual history about admitting we learned from other cultures, as if acknowledging Egyptian or Babylonian influence somehow diminishes Greek achievement. But that's ridiculous. Learning from others and building on their work isn't weakness, it's how knowledge actually advances. And here's what I want you to see. These controversies, these uncertainties, these debates, they don't undermine the importance of studying Pythagoras. They're part of what makes it interesting. Good scholarship requires intellectual humility. It requires saying, I don't know, when you don't know. It requires acknowledging uncertainty, while still making the best arguments you can from available evidence. So yes, we don't know exactly what Pythagoras personally discovered. Yes, our sources are problematic. Yes, he was influenced by Eastern traditions. But we do know this. Someone or some group in the Pythagorean tradition made revolutionary mathematical discoveries. They developed methods of proof that transformed mathematics. They proposed ideas about the mathematical structure of reality that shaped Western thought for millennia. And that legacy, however we attribute it, however we understand its sources, that legacy is real and enduring. So we've reached the end of our journey. We've followed Pythagoras from his birth on Samos, through his travels and education, to the founding of his school, through mathematical discoveries and mystical beliefs, political power and violent persecution, death and diaspora, and finally to his enduring influence on mathematics, philosophy, and culture. Now the question is, what does it all mean? Why does this matter? Look at this. Pythagoras remains a foundational figure in Western thought. His interdisciplinary approach continues to inspire thinkers who bridge seemingly separate fields. And then look at this breakdown. mathematics as primary influence, philosophy as secondary, music as significant contribution, astronomy as notable impact, and mysticism and politics as additional spheres. Let's be clear about what we're claiming here. We're not saying Pythagoras was right about everything. He wasn't. We're not saying he personally made every discovery attributed to him. He probably didn't. We're not saying his mysticism was valid or his politics were successful. They weren't. What we're saying is this: Pythagoras and the tradition he founded fundamentally changed how humans think about reality. Before Pythagoras, mathematics was practical. After Pythagoras, mathematics was theoretical, a system of proven truths about necessary relationships. Before Pythagoras, the universe was mysterious, controlled by gods, fundamentally incomprehensible. After Pythagoras, the universe was rational, governed by mathematical laws, accessible to human understanding. Before Pythagoras, philosophy was mostly about ethics and politics. After Pythagoras, philosophy included metaphysics, epistemology, the nature of reality itself, mathematics. This is where Pythagorean influence is clearest and most enduring. The Pythagorean theorem, the method of mathematical proof, the study of number theory, the application of mathematics to understanding nature, these are all part of the Pythagorean legacy. Every time a student learns geometry, they're inheriting Pythagorean mathematics. Every time a scientist uses mathematics to describe physical phenomena, they're working in the Pythagorean tradition. And this isn't just historical influence, this is active, ongoing, essential. Modern mathematics, physics, engineering, they all rest on Pythagorean foundations. The idea that you can prove mathematical truths with certainty, Pythagorean. The idea that mathematics describes nature, Pythagorean. The idea that studying patterns in numbers reveals deep truths, Pythagorean. Philosophy. The Pythagorean influence here is profound, but more indirect. Plato absorbed Pythagorean ideas about mathematics, the soul, and the structure of reality. Aristotle documented and critiqued Pythagorean philosophy. Neoplatonism incorporated Pythagorean mysticism. Christian theology used Pythagorean number symbolism. The questions Pythagoras raised about the relationship between mathematics and reality, about the nature of the soul, about how we can know eternal truths, these became central questions in Western philosophy. But here's what I think is most important about Pythagorean legacy: the interdisciplinary approach. His interdisciplinary approach continues to inspire thinkers who bridge seemingly separate fields. Pythagoras didn't see mathematics, music, astronomy, and philosophy as separate subjects. He saw them as different aspects of the same underlying reality. Study one deeply enough and you understand them all. And we need this approach today. We've become so specialized, so siloed. Mathematicians don't talk to philosophers. Scientists don't talk to humanists. Engineers don't talk to artists. But the most interesting problems, the most important questions, they exist at the intersections. They require multiple perspectives, multiple methods, multiple disciplines working together. When a physicist uses mathematics to understand the universe, they're being Pythagorean. When a musician understands harmony through ratios, they're being Pythagorean. When a philosopher asks about the relationship between abstract truth and physical reality, they're being Pythagorean. When anyone looks for underlying patterns, for mathematical structure, for rational order and apparent chaos, they're being Pythagorean. And Pythagoreanism shows up in the weirdest places. Computer science, Pythagorean, it's all about mathematical structures and logical proof. Cryptography, Pythagorean, number theory is essential. Music production, Pythagorean, still using those ratios. Architecture, Pythagorean, geometry and proportion everywhere, even your GPS calculating the shortest route. That's using the Pythagorean theorem 2,500 years after the guy died. But beyond the practical applications, Pythagoras left us with profound questions we're still grappling with. Is mathematics discovered or invented? Does it exist independently of human minds, or is it a human creation? Why does mathematics describe physical reality so perfectly? Is the universe fundamentally mathematical, or is mathematics just a useful tool? What's the relationship between abstract truth and physical existence? Between the eternal and the temporal? Between the necessary and the contingent? And here's what's remarkable. We don't have complete answers to these questions. 2,500 years of philosophy and science, and we're still debating them. But the fact that we're asking them, the fact that these questions make sense to us, that they seem important, and profound. That's the Pythagorean legacy. And let's not forget, Pythagoras was human. Flawed, limited, wrong about many things. He believed in reincarnation and sacred beings. He created an exclusive society that provoked violent backlash. He mixed brilliant insights with mystical nonsense. But that's actually encouraging, isn't it? You don't have to be perfect to make a lasting contribution. You don't have to be right about everything to be right about something important. Pythagoras got the big thing right. Mathematics reveals truth about reality. That insight, combined with the method of rigorous proof, was enough to change the world. So what does this mean for you? Why should you care about some Greek guy from 2,500 years ago? Here's why. Because the questions Pythagoras asked are your questions too. When you wonder how the universe works, you're asking Pythagorean questions. When you use mathematics to solve problems, you're using Pythagorean methods. When you look for patterns, for order, for rational explanations, you're thinking like a Pythagorean. And here's what Pythagoras would tell you, if he could. The universe is comprehensible. Reality has structure. Truth can be discovered through reason. You don't need mystical revelation. You don't need to be part of an exclusive society. You don't need a golden thigh. You need curiosity, reason, and the willingness to think carefully about difficult questions. This is the democratic legacy of Pythagoreanism, even though Pythagoras himself wasn't particularly democratic. The mathematical truths he discovered don't belong to an elite. They belong to anyone who can understand them. The methods he developed don't require special initiation. They require clear thinking and logical reasoning. The questions he raised aren't mysteries reserved for philosophers. They're questions anyone can ask, anyone can think about, anyone can pursue. But with this empowerment comes responsibility. Because if the universe is rational and comprehensible, then we're responsible for understanding it. If truth can be discovered through reason, then we're responsible for thinking carefully and honestly. And that's what Pythagoras really left us. Not just theorems and discoveries, but a project. The project of understanding reality through reason. The project of seeking truth through mathematics. The project of finding order in chaos, pattern in randomness, meaning in the structure of the universe. That project is ongoing. Every mathematician proving a new theorem is continuing it. Every scientist discovering a new law of nature is advancing it. Every student learning to think logically and reason carefully is participating in it. So yes, Pythagoras died in exile. His school was destroyed. His political dreams failed. His mystical beliefs were largely abandoned. But his mathematics endures. His methods persist. His questions remain. His vision of a rational, comprehensible mathematical universe became the foundation of Western science and philosophy. And 2,500 years later, we're still using his theorem, still asking his questions, still pursuing his vision of understanding reality through mathematics. That's not just survival, that's triumph. Not through political power, not through force, not through mystical authority, but through truth, through the simple, profound fact that he was right. Mathematics does describe reality. The universe does follow rational laws. Truth can be discovered through reason. And that truth, that insight, that vision, it's immortal. Not because Pythagoras was perfect, but because it's true. And truth, as Pythagoras understood, is eternal. So the next time you use the Pythagorean theorem, remember, you're not just calculating the length of a line. You're participating in a 2,500-year-old conversation about the nature of reality, the power of mathematics, and the human capacity to understand the universe through reason. And that connection between ancient insight and modern understanding, between one person's discovery and humanity's collective knowledge, between the eternal truth and your own thinking right now, that's the enduring legacy of Pythagoras. Not bad for a guy who was afraid of beans. Thank you.